Right, I have a pre-lecture, well actually a pre-announcement. On Wednesday, I will announce the semester writing project. So, remember, you have a project due this semester, which is 10% of your grade. And I will announce it on Wednesday. So, I'm just announcing that I'll announce it. Okay, let's get back to rotational motion. So, let's put the weekend out of our heads, unless we spent that studying physics, and go back to where we were. Right, so we covered a bunch of stuff last week, but what I want you to take away from it, like for today, is that B equals R omega, which means that when we're talking about rotation, right, we have to talk about the rotational speed of an object, right, the rotation rate. That is what we call the angular velocity. The symbol is that little w, it's called omega, it's a Greek w. And the important thing is that the angular velocity can be related to the linear or the tangential velocity, right, which is measured in meters per second, how fast an object is moving. Okay, and the relation is that V equals R omega, right? R is the distance of the point we're considering from the axis of rotation. Right? It stands, I mean, it's got the same alphabet as radius, but it's really just a distance. It's a radially measured distance of the point we're considering from the axis of rotation. Okay? And the other thing I want you to remember, of course, are units. Omega is measured in radians per second. That is when this relation is true. Okay? So if you're going to use V equals R omega, remember, use omega in radians per second. Okay, so we did this in terms of analogs to kinematics, right? Or analogs to translational motion, which is moving in a straight line, right? The same kinematic equations apply as soon as you substitute the relevant angular quantities, right? So we're not going to do too much rotational kinematics, which is basically just describing the rotational motion of an object, similar to describing the translational motion of an object. We're going to focus a little bit more on dynamics, which is today, as in why stuff rotates. Okay, before we actually move on to that, when we discussed translation, right, Newton's first law was the law of inertia, right, which basically said that an object will continue in a state of constant velocity, right, unless acted upon by an external force. Everyone remember that part? Okay. What physical quantity measures inertia? Mass, right? We all remember that? Okay. Now the question becomes, what physical quantity measures rotational inertia? Right? So inertia, if you remember, right, the reason we said mass is a measure of inertia is that the more mass an object has, the harder it is to get it to start moving or to stop it from moving. Right? If it's already moving, it has more mass, it takes more effort, more force on my part to stop it or change that state of motion. Right? If it's at rest and it has a lot of mass, right, like pushing that big dog, it's got more mass, so it's got a lot more inertia. Now, is the same thing true of rotation? Right? Now, when we're talking rotation, it's not so much getting the object to start moving in a straight line that's important, it's getting the object to start rotating that's important. Right? When we talk about rotational inertia, what we're talking about is the ability of an object to maintain its state of rotational motion. Everyone with me so far? Okay, so let's consider this. It's a hammer, right? The nice thing about being a physics professor, you can literally walk down the hallway holding this and no one blinks twice. Okay, I'm going to rotate it, right? If I rotate it like this, that's one way of rotating it without breaking my wrist. Right? So if I was going to try and stop this thing's rotation, right, it has a certain amount of inertia, correct? The amount of force I need to apply to get it to change its state of rotation depends on how much inertia this has, right? Correct? Now, if I hold it here and swing it, is it easier or harder? It's easier, right? It takes a heck of a lot less effort to stop it from rotating. It takes a lot less effort to start it rotating. Right? Same mass. Correct? Does everyone follow that? Okay, what changed? where I'm rotating it. Correct? The only difference between this situation and this situation is where it's like the axis of rotation. Right? And what part of this object the axis of rotation goes through. So this makes sense to everyone? Right. Now this whole thing has some total mass, correct? Right? The more mass it has, in general, the more rotational inertia it should have. Correct? If this was a more massive hammer, right, this process would have a lot more inertia. Correct? Okay. So what matters is how this mass is distributed. Right? So what matters to rotational inertia is the distribution of the mass about the axis of rotation. Everyone following me? Right? The difference between this situation and this situation is that the mass is distributed differently around the axis of rotation. Correct? In this case, is more mass further away or closer to the axis of rotation? Further, right? When this is out here and I'm trying to do this, right? The mass is further away from the axis of rotation. Right? In this case, right, the mass that's actually rotating, right, is pretty light compared to the mass that's not. Right? So the mass is actually concentrated closer to the axis of rotation, making it easier to rotate. Everyone with me so far? Right? So the rotational inertia, right, the quantity that measures the amount of rotational inertia that an object has depends on its mass and depends on how that mass is distributed. Right? Unlike linear inertia, right, where we're just trying to start an object moving, like and stating, where all that matters is how massive it is. Right? When it comes to rotation, it's not just a question of how massive the object is, right, but it's also a question of how that mass is distributed about what we're trying to rotate it. Everyone with me? Okay, now a little bit of math. So inertial mass basically tells you how difficult it is to accelerate from constant velocity, and rotational mass tells you how much rotational inertia it has. So the quantity we call rotational mass is something called moment of inertia, right, or rotational inertia. Another way to think about it is, if you guys remember what CDs or DVDs were. I'm guessing DVDs, at least some of people in your generation might remember those. I'm getting old. Okay, so if you decide to drill a hole through DVDs and rotate them, right, it matters where they are compared to where you're rotating them. Right? Consider hitting something with them. Right? So when you smack it, right, if it's further away, it takes more force, applies more force. That makes sense? If it's up close, not that much. Right? If you wanna, like, if you play any racket sports, you wanna get a good hand extension. Right, that's the same concept, right? Okay. So now a little bit of the math. The moment of inertia, the symbol for it is I. Okay? It's called rotational inertia, it's called moment of inertia, rotational mass, right? I'm going to be sticking to calling it moment of inertia, which is what your book calls it. Okay? We define the moment of inertia as this funky looking quantity, sigma mr squared. Okay? The idea here is that every mass of some mass m, right, some distance r away from the axis of rotation, contributes a certain amount of inertia. Right? That amount of inertia is mr squared. Okay? If I have an object which is made up of a bunch of these masses, then the total inertia is the total contributions of all those masses. Right? So, makes sense to try and do this with a diagram. Let's say I have a hoop, right? It's a hoop of mass m and radius r. Now, with a hoop, everyone knows what a hoop is, right? All the mass is concentrated at the edge. Correct? So if I consider the moment of inertia of this system, right, this object, about this axis, so it's rotating like this. Everyone follow that? Okay. Then some mass m here is a distance r away from the axis, right? So it contributes an amount mr squared. Some other mass m here is also a distance r away from the axis, so it contributes mr squared, right? And so on, right? I can break this ring up into a bunch of little m's, right? Correct? It's a hoop. I can think of it as made up of little m's, all located a distance r away from my axis of rotation. Everyone with me so far? Okay. And then I just add them up, right, to get the total moment of inertia, because the total moment of inertia is sigma mr squared, right? So it's the sum of all of these. So when I add up all of these, I get m plus m, all those m's, times r squared, right? The sum of all those m's is capital M, which is the total mass of that hoop. Right? So the total moment of inertia of a hoop about an axis passing through its center of mass is mr squared. Does everyone follow this? Now, it gets more complicated very quickly. This is the simplest system that we can figure out, right? If instead of a hoop, I have a disk, right, of mass m and radius r. Okay, so now the difference between a hoop and a disk is the disk has mass in the middle, right? Correct? Okay, if I were to try and do the same thing here, I run into a problem pretty quickly. Right? If I break this up into a bunch of little m's, right? Let's call that m1, m2, m3, and so on, right? I break this guy up into a bunch of little m's, right? And I find the total contribution to moment of inertia from each of these. Everyone with me so far? Right? So now what that would be is m1 is some distance r1 away, m2 is some distance r2 away, m3 is some distance r3 away. So I would start looking like m1 r1 squared plus m2 r2 squared plus m3 r3 squared, and so on for all the little m's that make up this disk. Right? But I can't factor anymore. Right? All those little m's are at different distances from the axis of rotation, so I can't factor the r out and solve like I did the last one. Does everyone follow this? Right? In order to actually solve this, I have to use calculus, which luckily you don't. But what I do want you to get from this is compare. In which case, the solid disk or the hoop, right, same mass and radius, would you have a larger I? Look at those numbers. The total mass is the same, right? If I could factor the r's out, right, then all those m's would come out and add up to the same big number, right? Correct? The mass of the disk hasn't changed, right? But look at these r values, right? The maximum value that the furthest some mass can be from the axis of rotation on the disk is r, right? That's if it's at the edge. Everyone with me? But all these other r's, r1, r2, r3, they're all less than that maximum r, right? Correct? So, this second summation involves sums that are smaller than all the sums in my previous summation. Right? For the hoop, every single piece contributed as much rotational inertia as it could. Right? Because it's sitting as far away as possible from the axis of rotation. Does that make sense? Right? All those little m's that made up the hoop contributed m capital R squared. Right? Where r is the radius. Correct? So they're all sitting at the edge. For the disk, on the other hand, right, only the one sitting at the edge contributed that much. Everything else contributed less. Right? Because it's closer. Does that make sense? It's the same thing as the hammer, right? In this scenario, this mass, which is big, right, contributes m r squared, to the rotational inertia of this system. With me so far? If I hold it here and swing it, this mass, which is still really big, contributes mr squared, but r is now close to 0. Right? Because it's now my axis of rotation. Does that make sense? So this light chunk here is contributing a little. Right? But it's a heck of a lot easier to rotate it this way than it is to rotate it this way. As you can see, I kind of need two hands. Everyone with me? Right? And that's what this is trying to tell you. Right? All of this math and the calculus that goes with it, right? All of it just tells you that if the mass is closer to the axis of rotation, right? Like it's closer to what it's rotating about, it has less rotational inertia. Right? If the mass is further away, it has more rotational inertia. This makes sense? Okay. Let's get back to the presentation. Right. So I will not be expecting you guys to actually calculate moments of inertia. These are moments of inertia of different shapes for different axes of rotation. Okay? I do expect you guys to be able to identify common objects as common shapes. Right? For example, if I'm talking about the tires on a car, right? And I want to find the moment of inertia, right, for that rotating system. It probably doesn't make sense for me to use a sphere. Right? The tires of a car are not spherical, they're more like cylindrical. Right? You could use an approximation like a thin disc, or you could use an approximation like a hoop. Right? Either of which is fine depending on the kind of tire it is. Everyone with me? But a sphere is not. Right? So those kinds of distinctions. And I know calculus gets a little like, gets a bad rep, but it's really just an easier method of trying to figure out what happens when things get really, really small and you want to add them up. Okay, and that's what was done for all of this. Right? It's that sigma mr squared. Right? And you apply that for different shapes. Right? You know the distribution of the mass about that axis. Right? You can calculate the moment of inertia. Everyone with me so far? Okay. Let's see if you guys are ready. I opened the question, yeah. See, this time I'm waiting for the responses to actually go up before I check and see where you guys are at. Very good. Right, that fixes that. Right, closer to the axis of rotation, less inertia. Right, further away from the axis of rotation, more inertia. Okay? Right, I'm going to close this, so please click something. Okay, now I'm asking you to consider two different objects, right? They're both spherical, right? Two spheres. One is hollow, one is solid, right? So one is like a basketball, the other is like a marble of the same mass and radius. Now tell me, which one would have a greater moment of inertia? In which case is the mass further away from the axis of rotation? Right? That's the question you want to answer. Right? Consider a hollow disk. Right? So all the mass of a hollow disk is as far away from as it can get, right? Correct? While as opposed to a solid sphere, right, there's stuff in the middle. It's got filling. Does that make sense? So one should be able to find that your responses are correct. Yes, 60% of you are on the right track. The hollow stuff is further away, right? So greater moment of inertia. Right, click something. Okay, now we get to rolling without slipping. So for the purposes of this course, when we discuss rolling motion, we're not going to discuss slipping, right? Because slipping involves translating along with rolling, right? But your general rolling without slipping, you have your normal translation which accompanies the rolling, right? An object is rolling, it is also translating at the same time, right? And that rotational motion can be linked to this translational motion when the object doesn't slip. Everyone with me so far? Okay. We've already discussed V and omega, right? So V is your translational velocity, R is the radius, omega is the angular velocity, right? And we considered that if I have an object rotating, right, with some angular speed omega, some point here, a distance r away, is moving with a linear speed of v equals r omega. Correct? Everyone with me so far? Right. That v is also the translational velocity of this object. Right? It's how fast this object is moving linearly. Does that make sense? Right? As an object rotates, right, as this slide shows you, if it's rotating, right, it's covering delta theta over delta t. That's the omega it has, right? So it's covering a certain delta theta in a certain amount of time delta t, right? As it rolls and covers that delta theta, it's covered a certain length. Everyone agree? Right? That length is the length of the arc that rolled, right? Does everyone follow that? Right? It's like however much arc rolled is the length actually moved. Right? And as we discussed last week, right, as long as we measure omega in radians, right, as long as we measure theta in radians, right, and omega in radians per second, as long as we measure omega in theta in radians, right, then the length of arc can be related to the radius and the angle, right, as r del theta, which gives you v equals r omega. Right? So v equals r omega is still true for an object that is rolling without slipping. Everyone with me so far? Right? So remember this relation, it's going to help, okay? That the speed of an object, the linear speed of an object that is rolling is directly related to its radius and its angular speed, right? And it's v equals r times omega. Everyone good so far? Okay. Right. So if we go back to our table of quantities, right, we can now add a new one, which is every time we talk about mass in translational motion, in rotational motion, I should be talking about rotational inertia, moment of inertia, I. Right? Just like every time we talked about linear speed, the rotational analog is angular speed. So we think about angular speed instead. Now, every time we talk about mass for translation, when it comes to rotation, we think about rotational inertia. Right? It measures the same analogous quantity. Okay. Now, an object that is rotating, right, is undergoing some kind of motion, right? So it has the ability to do work, right? Does everyone agree? A rotating object has energy, right? It has the ability to push stuff out of its way, so it has the ability to do work, and that means it has energy. And the question becomes, what kind of energy? And it's energy due to its rotational motion, right? So that kind of energy is a form of kinetic energy. Right? But it's not translational kinetic energy. Right? Translational kinetic energy measures the amount of energy that an object has because of its translational speed. Right? It's moving. Right? Rotational kinetic energy measures the amount of energy an object has because it's rotating. Does that make sense? So if I have an object that's doing both, right, like a ball rolling on the floor, right, it has two kinds of kinetic energy. One is its translational kinetic energy, right, 1/2 mv squared, and the other is its rotational kinetic energy. Everyone with me so far? Okay, the math part of rotational kinetic energy is very straightforward. We know that the translational kinetic energy is 1/2 mv squared, right? The rotational kinetic energy is just replace the quantities with their rotational analogs. Okay, so half of course has no rotational analog, so half stays half. M becomes I, right? As we move from translation to rotation, M is replaced by moment of inertia, I, right? And V is replaced by angular speed, omega. That makes sense? Right? So an object's rotational kinetic energy is 1/2 I omega squared. Right? The greater the moment of inertia it has about a specific axis, the more kinetic energy it will have. Right? Because the harder it is to change that. Right? The faster it's rotating, the more kinetic energy it will have. Right? More ability to do work. Everyone with me so far? So the kinetic rotational energy is 1/2 I omega squared. If an object is just rotating, it will only have rotational kinetic energy. If an object is rotating and moving, it will have both rotational and translational kinetic energy. If an object is not rotating and just moving, it has only translational kinetic energy. Everyone with me so far? Okay. Let's try this one. That is your rotational k. It's 1/2 I omega squared, right? In this question, you're given 4 objects which have the same rotational kinetic energy, right? And I'm giving you the moments of inertia of all of these. So which one must have the lowest angular speed? You can also think of this question in terms of its translational analog, right? If I was asking you, I gave you, like in this question I give you I's, right? Translational analog, I'd give you M's, correct? If I gave you a bunch of masses and said they all have the same kinetic energy, right? Which one has the lowest speed? The answer would be the heaviest, right? Correct? In order for all those masses to have the same kinetic energy, right? The heaviest mass must be moving the slowest. Everyone with me? Put that into its rotational analog, right? All of these objects have the same rotational kinetic energy, right? So the one with the highest amount of inertia, right, must be the one that has the lowest angular speed. Everyone following me? Right? So since k is constant, right, as I goes up, omega must go down if k is fixed. So since in this case all these objects have the same rotational kinetic energy, right, the one with the greatest inertia must be spinning the slowest. Okay? Right. Click something. Yes, I believe that's correct. Okay. Now, we discussed kinetic energy. The next topic, of course, must be energy conservation, right? So energy conservation still applies. And if you guys remember the law of conservation of mechanical energy, right? K plus U, right? The total kinetic energy plus the total potential energy of a system is conserved in the absence of any dissipative force. Correct? If I have no friction, I have no air resistance, I have no stuff doing work on the system, taking work out of the system, right? The only forces acting on it are conservative, right? Then all I get is K and U interchange between each other, but the total K plus U stays the same, right? The total energy of the system stays the same. The same must be true if an object is rotating, right? As long as I can account for the amount of energy that's in the rotation of the object, I should still be able to conserve energy, right? All I'm doing here is adding another kind of energy, right? Now we are considering an object has the ability to rotate, right? That rotation takes energy, so I need to account for it in conservation of energy. Everyone follow that? Okay. Translationally, of course, we only have typically the translational kinetic energy, and that's 1/2 mv squared. Now we're going to add the rotation, which is 1/2 I omega squared. Okay, so consider a sphere that rolls down a ramp without slipping. And it has an initial height h. It's important to have that condition. It's rolling without slipping. There's a couple of things it does, right? First off, if it's rolling without slipping, I know that its tangential speed v is equal to r times omega. Correct? Right? The second thing, if it's rolling without slipping, I don't need to worry about friction. Right? Friction does work on a rolling object when it slides. Kinetic friction comes into play when objects start sliding, right? Correct? Static friction doesn't do work, right? Static friction, there's no motion. Right? But kinetic friction comes into play when two objects slide with respect to each other. So if I'm conserving energy and I want to neglect friction, right, I can't have this thing slipping. Right? It has to be rolling without slipping. That's when I can conserve energy. Everyone with me so far? Okay. So all this thing does is it rolls down down from some initial height h on an incline. And if we did this earlier, right, we know that at the very top, if it started from rest, it only has gravitational potential energy, mgh. Right? It has some fixed amount of energy. And that's the total energy it will have at the bottom, 1/2 mv squared. Correct? That's when it wasn't rotating. Everyone with me so far? So now, its total energy is still the same, right? It still has mgh right at the very top. But at the very bottom, it has two kinds of kinetic energy. Rotational and kinetic. Everyone follow that? Okay. So we can conserve energy that way. Right? I can equate these two terms to each other. The total energy at the top is mgh. The total energy at the bottom is 1/2 mv squared because it's moving with some translational speed, and 1/2 I omega squared because it's rotating. Everyone with me? And the total of the kinetics must equal my potential. Right? From conservation of energy. Okay? Before we get to this question is actually a little bit of math. But before we get to this question, let's consider two objects. If I have a ball, right, a spherical ball, roll down an incline without slipping, right, and I have a block of mass m, right, move down the same incline with no friction. Okay, which one gets to the bottom first? Or do they both get to the bottom at the same time? This is not an easy question. I want you guys to think about it. What I'm asking is, I have a solid block which slides down an incline without any friction, no friction. Okay? And I have a ball that rolls down the incline. Right? Which one gets to the bottom first? Another way of asking that question is, which one is moving faster at the bottom? Or are they moving at the same speed at the bottom? How many people think they're moving at the same speed at the bottom? Okay, that's a very encouraging sign. Maybe. Maybe. Most people just equate it, like the total energy is the same, and so it must be moving the same speed at the bottom, which is not necessarily true. How many people think the block gets there first? How many people think the ball gets there first? Okay, I've listed 3 options. I counted maybe 20 hands going up sum total for all 3 options. If there's another option that you guys are imagining, now would be a good time to share it. Let's try this again. How many people think both reach at the same time? I've already said that's the wrong answer, so good. How many people think the ball reaches first? How many people think the block reaches first? Good. I have a minority that is correct. The block will reach first. Can someone tell me why? Like I said, this is a complicated question. What is true of the block and the ball when they're at the same height?
Well, for all the block, all its velocity would be in the transition velocity, so it has a greater speed. The circle loses some of its velocity.
Very good. So what he said was, for the block, all of its energy, right? Both the block and the ball start from the same height h, right? So they have mgh. They have the same total energy to start with. Correct? But for the block, all of that energy goes into its translational kinetic energy. Right? It doesn't rotate. Correct? So if it had 10 joules to start with, it has 10 joules of translational kinetic energy at the bottom. Everyone with me so far? Right. Now, if I consider the ball, right? It had 10 joules to start with. But at the bottom, that 10 joules is translational kinetic energy and rotational kinetic energy. Right? So, it has some non-zero rotational kinetic energy, let's say 3, which means its translational would be 7, which means it's not moving as fast as the block. Does that make sense to everyone? It's still an accounting process, right? The rotating takes energy. Right? I can't be moving as fast while rotating because I need, unless I have more energy. Right? If I have the same amount of energy, right, then the one that has more rotation has less translation. Everyone with me? Right? Conservation of energy is literally like balancing a checkbook, which you can say is your takeaway soft skill from this. But okay. Now, sadly, we do have to do a little bit of math. So follow along. I have a uniform disk and a hoop, right? So what's the difference between a uniform disk and a hoop when it comes to rotation? Right, so the hoop has a greater rotational inertia. Right? The difference between a mass, like a disk and a hoop, is the rotational inertia, right? The hoop will have a greater rotational inertia, the disk will have less. And this question, like all these questions, will give you the rotational inertia. So this question tells me that the rotational inertia of the hoop, right? So this is hoop, is m r squared. The moment of inertia of the disk, I disk, is 1/2 mr squared. Right? And this should make sense. The hoop has a greater moment of inertia than the disk, right? Mass is concentrated further away. Now, in order to solve this question, we set it up exactly like we would a normal conservation of energy question, right? I have something that starts from a height h, right? So that's over there, and then it's over here. So those are my two positions, right? So I'll say E1 here and E2 here. If I can conserve mechanical energy, then E1 is equal to E2. Everyone agree? Right? In the absence of dissipative forces, the total energy at the top is equal to the total energy at the bottom. Okay? Let's say that this object is rotating. So it's either the hoop or the disk, right? And we'll substitute later for hoop and disk. Right. So over here, E1 is K1 plus U1, right? At the very top, it starts from rest, so its kinetic energy is 0. Right? By the way, you may have homework questions where it doesn't start from rest at the top, right? In that case, you have to add the kinetic energy it already has. Right? Find the total energy at one position and equate it to the total energy at a different position. Okay? So the total energy here is 0 plus U1, which is the gravitational potential energy, which is just mgh. Everyone with me so far? And that's true for the hoop and the disk, both of which have the same mass center. Okay? Now, at the bottom, E2, it's still K2 plus U2. right? At the bottom, it has no U2, right? It has no MGH. Okay, it's already there. It has K though, but K2 is what? 1/2 mv squared or 1/2 mv squared plus 1/2 I omega squared? Is the object rotating at the bottom? It's either a hoop or a disk. Is it rotating at the bottom of the incline? Yes, it rolled down the incline, so it has rotational kinetic energy. Does that make sense? It's an object that is rotating and moving, right? So I have to account for both those energies, right? And that sum total must still equal what I had to start with. So I have 1/2 mv squared plus 1/2 I omega squared. That is my energy at the bottom of the incline. Everyone with me so far? Okay, now I apply conservation of energy. This guy must equal this guy, right? No dissipative forces. So I can write mgh is equal to 1/2 mv squared plus 1/2 I omega squared, right? And that much is true for both the hoop and the disk, correct? The difference between the hoop and the disk is the I. Right? So now let's do the hoop first. Okay? So let's say for the hoop, right, I get mgh, that's still the same, plus 1/2 mv squared, that's still the same, plus 1/2 I. I for the hoop is mr squared. Correct? Right? The moment of inertia for the hoop is given to be that much. I substitute that at this point. Right? This times omega squared. Everyone with me so far? Right? The only stuff I've done right now is substitute the moment of inertia of the hoop to start discussing specifically the case of the hoop. Okay? Now look at this term r squared omega squared. V is equal to r omega, right? Is this object roll down without slipping? Its translational speed v is r times omega, right? So that term r squared omega squared is nothing but v squared, right? So, and I can substitute that. And by the way, when this question comes on exams, most people forget this part, right? This guy, r omega is v, so r squared omega squared must be v squared. Everyone with me so far? Okay, now this becomes mgh is 1/2 mv squared plus 1/2 mv squared. Everyone with me so far? So this becomes, and this is now v of the hoop, right? Because we've been discussing the hoop. So mgh is equal to mvh squared. M goes away, and we'll discuss that in a minute. But the speed with which the hoop reaches is under root gh. Everyone with me so far? Right? It's just algebra. Okay? And all we did was substitute the value for the moment of inertia of the hoop. Right? And then we further substituted that since this object rolls without slipping, its translational speed is r omega. Okay? We do the exact same thing for the disk. So we start at the same location. Right? For the disk, I still have mgh equals 1/2 mv disk squared plus 1/2 I disk omega squared. Right? That's the disk conservation of energy. This now becomes mgh equals 1/2 mvd squared plus 1/2 I disk is 1/2 mr squared. Right? So I since I'm now talking about the disk, I substitute the moment of inertia of the disk. Right? And I end up with that same term, r squared omega squared. Right? The only thing that changed is the numerical factor in front of it. So this becomes mgh equals 1/2 m speed of the disk squared plus 1/4 m speed of the disk squared. Right? Half times a half is a fourth. Everyone with me so far? Right. So add a half to a fourth, that's 3/4. So I get mgh equals 3/4 mvd squared. M goes away again, right? And vd comes out to be 4/3 gh under root, right? That's the speed with which the disk is moving at the bottom of the incline, right? And if we compare to the hoop, which one's greater? Which of these two numbers is greater? The disk, right? And this should make sense. The disk had the smaller rotational inertia, right? So even without doing the math, it is possible to guess that the disk will reach there first. Right? Just because the disk has a smaller rotational inertia, it will have lower rotational kinetic energy. Therefore, it will have more translational kinetic energy. Right? Meaning it's moving faster. Everyone with me so far? Okay. Now, mass cancelled out completely, right? These speeds depend purely on the height and how the mass is distributed. Right? So the mass and the radius are completely irrelevant. Does this make sense? So if the question was a marble and a basketball roll down the incline without slipping, which one gets there first? The one with the smaller moment of inertia, right? Smaller moment of inertia will get there first. It will have less rotational kinetic energy. Right? Smaller moment of inertia means mass is concentrated closer to the axis of rotation. Marble. Right? Basketball mass is further away. It's hollow inside. Correct? It's not the total mass which mattered. It's the distribution of mass which mattered. Does this make sense to everyone? Okay. We will continue with more fun stuff on Wednesday. And hopefully at the end of this week, we'll be done with rotation.
From what's on the syllabus, we're a little bit behind. So would it be that there's less material, or what the exam will?
The exam will only cover material aspects.
Okay.
I will talk about the exam.
Okay.